Hello. So in this video, we will try to derive the Bellman equations with the help of the law of iterated expectations. And the Bellman equations are basically trying to form a recursive relationship between the value function of the current state to the value function of the next state. So over here, I have shown a sample trajectory tau, which is basically the sequence of steps that happen when you are in a particular state and you take action on the state and you subsequently receive rewards for that. So the expression for the state value function, given that you are following a policy pi, is shown by this particular expression over here. And it is basically the expected return that you expect to receive if you begin from the state S and you then follow the policy pi optimally thereafter. So, so let's start by looking at the return. This return GT can be expanded as RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3 and so on till infinity, where this gamma is basically less than equal to 1 and more than 0. And what you can say is you can write this recursively as well, and this will be gt is equal to RT plus 1 plus gamma times gt plus 1, right? So let's substitute this expression in the original state value function, and then therefore our state value function will be equal to what? V pi of s is basically equal to the expected value of RT plus 1 plus gamma times GT plus 1, given that we start in the state small s at time step t. I'm going to omit the policy pi from now on for simplicity, right? So now, because of the properties of expectation, we can simply write this as expectation of RT plus 1 given ST is equal to S plus gamma times the expected value of GT plus 1 given that ST is equal to small s. So now we have two terms to deal with and we are going to deal with them separately. So let's first of all solve the first term, and the first term is basically expected value of RT plus 1 given ST is equal to S. Okay, so what we will do is we will now use the law of total expectation, and the reason why we are using the law of total expectations over here is that we want to find the expected value of RT plus 1 right now, but what we have conditioned it to is just the starting state ST. We have not specified any information about the action we have taken, and therefore what we need to do is we need to fix the action AT as well. And so for that, what we will do is we will say that this is basically equal to the expected value of the expected value of RT plus 1 given the state at time step t and the action at time step t, and this is conditioned over the fact that my state at time step t was equal to small s. And just to understand why we actually need this action AT for calculating this expectation is that if we simply try to use the definition of expectation over here, that it is a summation over all the rewards, a reward times the probability that we receive this reward given that I was in the state S, we do not have this probability density function with us. What we have with us is the system dynamics function, and let me also write that. So the dynamics function that we have with us is basically the probability of landing in the next state S prime and getting the reward R given that I was in the state S and I took the action A. So this is given to me, right? And I somehow want to calculate this. And this is not possible because I have not fixed the action A right now. Okay. So that's why we will have to take the expectation for the actions as well. And so therefore, what I can say is that the outer expectation is of course with respect to all the actions possible. And the inner expectation is like this. It is rt plus 1 given the starting state st and action at, and this being conditioned on st equal to s. If I open this up, this will be equal to summation over all the actions. Now, the probability of choosing this action conditioned already on the fact that my starting state was s, because see right here I have conditioned this evaluation on the starting state s, multiplied by again the expectation of rt plus 1 given that st is equal to s and at is equal to a, right? So now let's see. Basically, this probability of choosing the action A given that you are in some state S is your policy, right? Your policy will always tell you what action to take and with what probability if you are already present in a particular state. So we will replace that with pi. And then this expectation of rt plus 1, if we try to expand this just by the definition of expectation, then this would be summation over the rewards. Reward times the probability of getting this reward given that I was in the state S and I took the action A. So see, now we have the action fixed as well. And so we have moved one step closer to the dynamics function over here, right? And so what you can also see is that this particular probability over here is a marginal probability density function. And what we can do is we can write this as summation over all the actions, then summation over all the reward times, and now we will sum it over all the possible next states, right? So the probability of going in the next state and getting the reward are given state S and A. So this is basically equal to this particular term. So now this term is known to us. R is known to us because we are just calculating all the possible rewards, and this policy is also known to us. So now we can calculate the expected value of rt plus 1 given the state S properly. Now let's go on to the next term, and the next term number 2. The next term that we had was basically the expected value of gt plus 1 given that the previous state st was equal to small s, and again I'm omitting the policy pi. Now just to be clear, this expected value of gt plus 1, this return gt plus 1 will concern itself only with the rewards received from the time step t plus 2 onwards, right? And so just to be clear, this gt plus 1 is basically equal to rt plus 2 plus gamma times rt plus 3, so on, right? So if we see in the trajectory of our agent, we want to reach somewhere over here, right? And for that we will have to cover the starting state S, the action taken A, the state we land to, the action we take again, and then we will be able to determine rt plus 2 basically. So let's see. This is basically somewhere in most of the text we have seen that I saw that this was directly said to be equal to the state value function for the next state st plus 1, right, or s prime basically. And this is quite misleading because actually the state value function for the next state should be is expected value of gt plus 1 given that the state st plus 1 is equal to s prime. And so somehow they were not able to bridge the gap between this equation and this equation, right? So we will try to do that over here. And so now what we will do is that we will again use the law of total expectations, and then we would be saying that this is the expected value of the expected value of gt plus 1 given that I was in the state st and I took some action at, that is conditioned by the fact that st is already equal to some small s. And so again this is an expectation over all the actions, right? So if you open this up, this will be summation over all the actions, probability of taking this action given that you are in the state small s, expected value of gt plus 1, given that st is equal to s and the action taken was at is equal to a, right? And now again, I cannot simply expand this now. I cannot say that this is basically equal to summation over all the actions like this, and then summation over all the returns I'm getting, g times probability of getting this g given that I was in the state um, s in the previous time step and I took the action a in the previous time step. Because in order to know about the reward in the time step t plus 2, I will have to know about my current state in the time step t plus 1, right? So I cannot simply write it like this. So what I will do over here is that I will again apply the law of total expectation on this inner expected expectation value, and we will now apply this for the different possible values of the next state. So this is the expectation of the expected value of gt plus 1, given that you know the starting state, or you know the previous state, you know the action taken in the previous state, and you know the current state as well. And this is of course conditioned on the fact that your previous state is equal to small s and your action taken in the previous state is equal to small a, right? So now this will be equal to summation over all the actions, probability of choosing this action given the state. This is summation over all the possible next states, and this will be expectation of gt plus 1 given that st is equal to s, at is equal to a, and st plus 1 is equal to sum s prime multiplied by the probability that you land in the state s prime given that your starting state was s and took the action a. And you see again we have landed one step closer to the dynamics function that we had over here, because we now have conditioned it on the previous state and the previous action. And so now this is again a form of the marginal PDF, and so that will be solvable, right? And one more thing to note over here is that as you can see in this expression, we are trying to find the expected value of gt plus 1 given that you already know the previous state, the previous action, and the current state. However, this is an MDP and this follows the Markov property, and as per this you will not require the historical information about the states and actions in order to take an action in the current time step. If you know the current state you are in, you will be able to perform an action, and the presence of the information of the previous states and actions is not required, right? So given that you now already know the current state you are in for time step t plus 1, all the rewards following the time step t plus 1 can be completely determined with the help of this information alone, and you do not actually depend on st and at anymore now. This was not true in the previous case, that the expectation of gt plus 1 given the state st at a time step t. Then also I cannot say that gt plus 1 will not depend on the previous state st, because right now I have not conditioned the reward starting from time step t plus 2 on the current state. I only have information about the previous state, right? So this previous state will only determine the state at st plus 1, and that will completely determine gt plus 1. So unless I get the information about st plus 1, which I have got right now, I will not be able to say that gt plus 1 will not depend on st. So if we now say that this is basically equal to summation over all the actions, this is summation over all the next states, and this is just the expected value of gt plus 1 given st plus 1 is equal to s prime, and this is now basically summation over all the rewards, probability of going in the state s prime and receiving reward r given s at a. So this right here is basically your state value function for the next state s prime. So this is basically equal to summation over all the actions, and this is summation over all the next states and rewards. Probability of going in this next state and getting the reward R times the state value function for S prime. And so now we have solved for both the parts of the equation, and so now we can just add them up and we can multiply the second part with gamma, and what we will end up with is v pi of S is basically summation over all the actions and then we had R times probability plus gamma times and so we can now take a lot of things common outside. So this will be summation over all the actions is multiplied by R plus gamma times the value function of the next state. Right, so this is basically the Bellman equation. This is basically the Bellman equation concerning the value function of the states. And so now this Bellman equation will basically help in establishing a recursive relationship between the value of the current state and the value of the next state. And therefore, at any point, if you do not know what is the value of the current state you are in, but you know about the possible actions you can take and the possible next states you can land in, you can use the value function of the next states in order to calculate the value function of your current state. And one more interesting way that we can represent this equation is by the fact that you can say that the value function of the current state is basically equal to summation over all the actions you can take in the current state, all the rewards you will receive, and all the next states you can land in. The probability of taking a particular action in the current state and the probability of landing in the next state and getting the reward R, given that you are in the state S when you took the action A, multiplied by R plus gamma times the value function of the next state. So this is basically the expected value of this term over here for all the possible actions, rewards, and next states that you can have. So we have taken all the possible triplets of the action, reward, and the next state, and we have multiplied the probability of getting this particular triplet with the return that we can get. So now that we have covered the state value function for the Bellman equations, let's also cover the state action pair value functions for the Bellman equation. And what essentially is a state action pair value function is that it suggests how good is it for the agent to perform a particular action in a particular state. And this is basically given mathematically by the expected return that you will receive if you were present in the state S at time step t and you took the action A at time step t and then you follow the policy pi optimally thereafter, right? So now we also want to find a recursive relationship between the state action pair value function for the current time step and for the next time step. So for that, what we will do is we will again use similar expressions. We again know that gt is equal to rt plus 1 plus gamma times gt plus 1. So if we use that, then we can write that this is equal to expected value of rt plus 1 plus gamma times gt plus 1 given st equals s and at equals a. Right, so if I again open this up, I will end up with two terms, and The first term is going to be equal to what? The first term is going to be expected value of rt plus 1 given st is equal to small s and at is equal to small a. And this, as you can see over here, is quite similar to what we had in the case of the state value function, just that we now also have fixed the action right now. So it has become easier for us because we can now simply write this as summation over all the possible rewards r times the probability of getting this reward given that I was in the state S and I took the action A. Right, and this is again a marginal PDF, so we can write this as r times summation over all the next states probability S prime r given that I was in the state S and took action A. So this is the first expression, and for the second expression is expectation of gt plus 1 given that st is equal to s and at is equal to a. So this is again really the same thing as before, just that we now have also fixed the action, and so now we will only have to apply the law of total expectations once. So we will basically apply at once, where we will be iterating over all the possible next states. Expected value of gt plus 1 given the previous state, action taken, and the current state, and this is evaluated given the fact that my st is already fixed to be small s and at is already equal to small a. So this becomes equal to summation over all the next states, and the probability of going in this next state given that I was in the state S and took action A, multiplied by the expected value of gt plus 1 given that st is equal to s, at is a, and the current state st plus 1 is s prime, right? And so again, applying the same logic that we follow the Markov property, and therefore this gt plus 1 will not depend anymore on st and at, because we now have the information about st plus 1. We will get this is now expanded to summation r probability s prime r, and this is now expected value of gt plus 1 given st plus 1 equal to s prime. However, you can see that this is now equal to the state value function of the next state. So this is basically v by s prime. But what we need to do is we need to establish a recursive relationship between the current state action pairs value function and the next state action pairs value function. So we will have to again apply the law of total expectations, but this time on the actions that I can take on the state at time step t plus 1. So this will be summation over all s prime r and this is expectation over all the actions, let's say a prime gt plus 1 given st plus 1 and at plus 1 given the fact that st plus 1 is already fixed to be s prime. And now this will open up to summation over all the next actions possible, the probability of choosing this particular action a prime given that I am in the state s prime at time step t plus 1 times the expectation of gt plus 1 given that st plus 1 is equal to s prime and at plus 1 is equal to a prime. And this term over here is basically equal to q pi of s prime and a prime, right? So that is why this will become summation over all the next actions. And this is basically the policy applied for the state S prime. Right. So now once that we have got both the terms of the expression, we can collectively write the state action pair value function to be equal to summation over all the rewards and all the next states. We have probability as prime given that the state is take the action A plus summation over again all the next states and all the rewards, probability S prime and R given S and A times summation over all the next actions, probability of choosing the next this next action, and so now we can take a lot of terms common, and that will be summation over S prime and R, probability of getting the reward R and going in the state S prime given that I'm in the state S and I choose the action A, followed by R plus, now we also have a gamma term over here which gets multiplied, so this would be R plus gamma times summation over all the next actions possible, probability of choosing this action given that I have been in the state S prime times the state action value function for the next hidden action. So this is basically the Bellman equation derived for the state action pair value function as well. So by this we have completed the derivation of Bellman equations for both the state value functions as well as the state action pair value function. So thanks for watching the video.